Okay, so this is my initial value. This is the question that they have given us. Solve the following initial value problem over interval from t is equal to 0 to 2. That means this is a domain where y0 is equal to 1. So this is nothing but what? Initial value. Okay, and this is our main differential equation. So you have to solve this differential equation analytically and using Euler's method. So let us solve this. First, let us solve this analytically. So it's very simple. So I'll be using this notation for derivative y dash, Newton's notation, or the prime notation. Sorry, I think Newton's notation is different. Sorry, this is prime notation. So this is going to be y dash is equal to y t square minus 1.1. This is what they have given, and they have given us the initial condition, and they have given us the domain. Okay, so if you write it down this mathematically, you should write it down like this. T belongs to from 0 to 2 in the domain 0 to 2. Okay, so let us solve this differential equation analytically. So I think solving this analytically is going to be very simple. You first write down dy by dx y t square minus 1.1. So if you see here, I'm sorry, this is going to be t. So if you see here, by looking at this differential equation, you'll realize that you can solve it by separation of variables. So you are going to separate the variables. Let me write it down here. You are going to separate the variables. Dy upon y equal to t square. So once you separate the variables, you have to integrate on both the sides. Once you integrate, you will find out this comes out to be ln y. This comes out to be t cube minus 1.1 into t. I'm sorry, t cube divided by 3 into 1.1 into plus there will be a constant c. Now to remove this constant, what you are going to do? You are going to use the boundary condition. The boundary condition here is at x is equal to 0, y is equal to 1. Okay. So if you substitute x is equal to 0 and y is equal to 1, you'll realize the value of c that you are getting is 0. Okay. And if you do that, you'll find out that the equation that you're getting is y is equal to e raised to t cube divided by 3 minus 1.1 t. So this is the solution of unique solution of your differential equation. Now if you plot this differential equation, what you're going to get is a graph something like this. Okay, so when you plot this from in your domain, in the domain 0 to 2, okay, anyways, I'll show it here. In the domain 0 to 2, this is what your graph looks like. So this is known as your analytical solution. Now what we want is we want to find out the numerical solution using Euler's method for h is equal to 0.5. Oh sorry, h is equal to 0.5 and 0.25. Okay, now I think this is working. This is white, so I'll have to change the color. Yeah, 0 and 2. Now it's working. So let us solve this problem by Euler's method. Okay, so let's use this. So what is your differential equation? Y t square minus 1.1. This equation is nothing but equation of fxy. Okay, so understand one thing, when you say fxy is nothing but the slope or the differential equation. Okay, so t is from 0 to 2. Okay, and for the first part, what we are going to do is we are going to take h is equal to 0.5. So again, what is the formula for the Euler's method? New value is equal to old value plus the slope. The slope is nothing but this xi yi into h. Okay, so I think everything is known, but the only thing that we have to find out is we have to find out the slope. Okay, now there are many methods to do this, but what I will follow again here is a tabular approach. Okay, so the first variable I'll say is ti. Okay, now understand one thing. Your xi plus 1 is nothing but what? Xi plus h. So understand this thing. Okay, but again, in place of x we have t here, so t is our independent variable yi. Then what I need next is f of tiyi, which is this. Sorry, I wrote it down, function of xy, which is this is but ty, and this is what we are interested in, that is yi plus 1. Okay, now the domain is from 0 to 2, so you will start from 0. Okay, what is the step size? So again I'll remind you, x plus 1 is nothing but xi plus h. Okay, so you just have to go on adding the step size. So since here in this problem you are taking step size as 0.5, so if you take that step size, the next point is going to be 0.5, the next point is going to be 1.5, and the next point is going to be 2. Do we need to go beyond this? Obviously not, because if you see, the domain is from 0 to 2. You just have to be from 0 to 2. Now the next thing is we have to find out the value of yi. Okay, but if you see the question, they have also given us the initial value. What is the initial value? If you can recall from the problem, if you want I can just take back to the previous one. So this is the initial condition. Okay, so the initial condition is this, so which means at x is equal to 0, sorry, the independent variable is t, so at t is equal to 0, y is equal to 1. That means at t is equal to 0, y is going to be 1. Now what we have to do is we have to find out a function, substitute the value of tiyi in function of tiyi, okay, and get the value of this function, and this function is nothing but what? The slope. Now which is the equation of this function? Now if you see, this is nothing but the equation, so if you want you can write it down here properly if you want. Y t square minus 1.1. Okay, just write down I for if you want, for clarity. So what you are going to do is you are going to substitute 0 and 1 in this equation. So if you substitute that, you will find out the value that you are getting is minus 1.1. Okay, and this is our main equation. Okay, now if you see the next column, what you want is yi plus 1. So you have value of yi, you have value of function, you have the value of slope. So if you have both the values, what you're going to do is you're going to substitute those values in this equation. You also know the step size. Step size is 0.5, and you'll find out the value. So you'll realize that the value that you're getting, you'll find out that the value that you're getting is 0.45. Okay, so this is the value of y plus 1. Now for the next iteration, this value 4.5 will come here. Okay, I hope everybody is clear. So now what you're going to do, you're going to substitute this value and this value in this equation, and again you're going to find out the value. If you see the value, if you calculate the value, comes out to be this. Okay, again you know yi, you know this, you know this, you know this. Substitute these values, this and these values in this equation, and get the value. You'll find out the value that you're getting is 25875. Again this value will come here for the next iteration, 25875. Again substitute these two values in this equation, get the value. Okay, now again the next thing what you're going to do is you're going to find out, you're going to take this here. Okay, now you tell me, do we need to move ahead? Obviously we don't need to move ahead, because what we wanted the value of y from 0 to 2. Okay, and if you see here, what you have done is you have already calculated the value from 0 to 2, so you don't need to go any further. This is where you're going to stop. Okay, so this is the value that you're getting. Okay, now again what you're going to do next is, this is the first part. For second part, what you're going to do, you're going to substitute h is equal to 0.25. so again this comes out to be ti, it's going to be yi, then this is going to be okay. So you'll start at 0, then 0.25, you'll plus h, then you'll add h, then you'll add h, okay, and you'll just go on adding. Okay, so, and I think you can easily find out these values, and if you see, the graph that you'll be getting is going to be this. Okay, so this is your analytical. This is for h is equal to 0.5, and this is for h is equal to 0.25. Okay, so if you solve this and if you plot the graph, you'll get this graph. Okay, and this is for 0.5. so as you go on decreasing the value of step size, you're going to come here, and you're going to come here, you'll approach your analytical solution. Okay, so as you go on reducing your step size, you will approach the analytical solution. Okay, so this is how you have to solve a problem, an initial value problem, using Euler's method. I hope everybody is clear with this.